So let's continue on with our inner integral then. So at the end of the previous part, this is where we'd got to. So the first thing I'm going to do is pull out this 1 over cos theta plus sine theta to the power of d1 plus d2 over 2, because that's a constant with respect to this inner integral. So we'll pull it out of the inner integral and it will remain in the outer integral part. So we've got 1 over cos theta plus sine theta to the power of d1 plus d2 over 2. So we're going to have to remember when we put this back in to the outer integral that we need to bring this bit up there. And now let's consider what's left of the inner integral. So the integral from 0 to infinity of u to the power of d1 plus d2 over 2 minus 1 times e to the negative u du. Well, this, by definition, this is a gamma function. The gamma function, gamma of alpha, is defined to be the integral from 0 to infinity of u to the power of alpha minus 1 e to the negative u du. So this is gamma, where this is our alpha. So it's gamma of d1 plus d2 over 2. So you see we've now got this will all just become this constant value, which is gamma of d1 plus d2 over 2. And if you remember, right back up here, we've got in the denominator out here gamma of d1 over 2, gamma of d2 over 2. Now we're going to add in here gamma of d1 plus d2 over 2. So we've got the other part that we need to make the beta function of d1 over 2 and d2 over 2. In fact, it's going to be 1 over the beta function of d1 over 2, d2 over 2. So now putting our answer for the inner integral back into the whole thing that we're trying to calculate, which remember is the CDF of our random variable big S for a positive little s value, this is what we're going to get. So this over here, remember, this is the inner integral that we've now worked out. So that comes out as gamma of d1 plus d2 over 2, which is a constant with respect to the outer integral, so I've pulled it out. So I've now got this as my overall constant out the front, gamma of d1 plus d2 over 2 over gamma of d1 over 2 times gamma of d2 over 2, which is 1 over beta of d1 over 2, d2 over 2. So I'll replace this in a moment with what it is in terms of the beta function of d1 over 2 and d2 over 2. And now the outer integral is still here, so the integral from 0 to tan inverse of s of this bit remains. So we've got cos theta to the power of d2 over 2 minus 1, sine theta to the power of d1 over 2 minus 1. And now it's also over this bit that came from the inner integral, so this bit down here, which is cos theta plus sine theta to the power of d1 plus d2 over 2 d theta. So that's what I've now got to work with as my CDF. Now this looks like a bit of a nightmare. You might be looking at this integral thinking, oh dear. But remember, we're actually trying to find the PDF, so that's going to be our saving grace here, because we can now differentiate this mess. And the first fundamental theorem of calculus will save us, because we'll differentiate this and we'll never ever have to actually do the integral of this. So that's what we'll do next. So this is the CDF of our random variable big S. If we want to find the PDF of that, then now we differentiate this with respect to S. So we'll do that now, and this is what we get. So I've got this constant that can come out of the derivative, so it's just 1 over beta of d1 over 2 d2 over 2. And now the derivative of this thing with respect to s, so we can apply the first fundamental theorem of calculus to this. If it was just s that we had up here, then it would be really simple. It would just be this integrand evaluated at s would be the derivative of that. However, we've got tan inverse of s up here, so to differentiate that with respect to s, it will be the integrand evaluated at tan inverse of s times the derivative of tan inverse of s. We are applying the chain rule to this function. We're differentiating, if you like, firstly with respect to tan inverse of s, and then we're timesing that by the derivative of tan inverse of s with respect to s. So I could have written this out in full and it would have been a complete mess and it wouldn't have fitted in this space. To save myself, I have abbreviated tan inverse of s to this letter phi, which we've previously used to denote that angle, which is of course what tan inverse of s is. So Instead of writing cos of tan inverse of s here, I've just written cos of phi, and we're of course going to work out what these things are in terms of s in just a moment using a bit of triangle trigonometry and Pythagoras' theorem. So cos of phi, which is cos of tan inverse of s to the power of d2 over 2 minus 1, then sine of tan inverse of s, sine of phi, to the power of d1 over 2 minus 1, and then the denominator, cos of phi plus sine of phi to the power of d1 plus d2 over 2. So that's just this integrand evaluated at phi, which is tan inverse of s. And then I've times it by the derivative of tan inverse of s, which is 1 over 1 plus s squared. So this now is the PDF for my random variable big S when the value little s is greater than 0. So now a bit of trigonometry to work out what cos of phi and sine of phi are in terms of s. So remember, this is the triangle that is relevant here. We've got length 1 here on the adjacent, length s here on the opposite, and then we've got the hypotenuse here, and then tan inverse of s means this angle here. It finds that angle phi. Now, if we would then want to know what cos of phi, which is cos of arctan of s is, or what sine of phi, which is sine of arctan of s is, then we can just think about this triangle and think what cos of phi and sine of phi would be. So cos of phi is going to be the adjacent over the hypotenuse. By Pythagoras' theorem, the hypotenuse here has length the square root of 1 plus s squared. So cos of phi is therefore going to be 1, the adjacent, divided by the length of the hypotenuse, which is the square root of 1 plus s squared. So this is the formula in terms of s for cos of phi. So we just need to replace these cos of phi's with that. And then sine of phi is going to be opposite over hypotenuse, which is s over the square root of 1 plus s squared. So this is what we need to substitute in for sine of phi's here. And then we need to work that all through and see if we get something reasonably nice at the end, or something that resembles that formula that I had from Wikipedia. Of course, that's not the final F distribution. We do, remember, have to scale it by that constant that we left out for the final bit of tinkering. So I'm sorry for how squeezed in this is. I'm trying to write it in a space that's in view of what we previously had, so that it's not confused. I've changed colour. So the next formula is in red, distinguishing it from the previous formula. So here's the previous formula, and now we want to make these substitutions into it. So we've still got the 1 over beta of d1 over 2 d2 over 2, and then here is the cos of phi replaced with 1 over the square root of 1 plus s squared, still to the power of d2 over 2 minus 1, and then we've got sine of phi, which is s over the square root of 1 plus s squared to the power of d1 over 2 minus 1, and then we've got over, and now we've replaced cos of phi plus sine of phi with 1 plus s, so we can combine these two together into 1 plus s over the square root of 1 plus s squared, all to the power of d1 plus d2 over 2, and then I've pulled this bit into this denominator, so we've got 1 plus s squared there. So hopefully you're happy with that. That's our PDF now. So I've changed colour again, so the next part is in blue. So we've still got 1 over beta of d1 over 2 d2 over 2. And now what I've done is I've gone to this bit here and I've separated it into two parts. So I've separated it into s to the power of this times 1 over the square root of 1 plus s squared to the power of this. And then I've combined that bit which is 1 over the square root of 1 plus s squared to the power of this with this bit here. So the s to the power of d1 over 2 minus 1 is here, s to the power of d1 over 2 minus 1. And then this bit here is the combined 1 over the square root of 1 plus s squared from here and the 1 over the square root of 1 plus s squared from here. So I just have to add their two powers together, which gives me d1 plus d2 over 2 minus 2. So hopefully you don't mind me doing that. I've just manipulated this numerator. And now I'm going to manipulate the denominator again. So I'm going to split this bit into two separate bits again. So I've got 1 plus s to the power of d1 plus d2 over 2, which is here, times 1 over the square root of 1 plus s squared to the power of d1 plus d2 over 2. And I've still got the 1 times 1 plus s squared here. And now my claim is that this bit here cancels with this bit here, because if you think about what this minus 2 is, if you split this into this to the power of this times this to the power of this, then this to the power of minus 2, you'd flip it, so you'd get the square root of 1 plus s squared, without not 1 over it, but just it, and then you'd square that, so you'd just get 1 plus s squared here, which would cancel with this, so you'd have this thing, 1 over this, to the power of d1 plus d2 over 2 times 1 plus s squared. I could rewrite this as exactly this. So this will cancel with this, and isn't that beautiful? Because now all we're going to be left with is this bit here, which is still a little bit complicated looking, but it's a lot better than what we had. So we're very close now. So I've written out what we've got left here. So we've got 1 over beta of d1 over 2 d2 over 2. And now this is the bit we've got left. What I have done is I've just pulled this 1 over s out from here. So we've got s to the power of this times s to the power of minus 1. I've written that s to the power of minus 1 as 1 over s. So I've got the 1 over s there. And then I've noticed that this thing is s to the power of d1, then to the power of half. You can rewrite it as that. And this is 1 plus s to the power of d1 plus d2, then to the power of a half, because if you raise to an exponent and then raise to another exponent, it's the same as raising to the product of those two exponents. And then I've factored out that to the power of a half to write it like this. So we've got s to the power of d1 over 1 plus s to the power of d1 plus d2, and then all of this to a power of a half, which is the square root. So hopefully you can see that this thing is just this to the power of a half, which is the same as this to the power of a half over this to the power of a half, which if you then write it back again as, if you multiply out the sequential exponents, is the same as what we've got here. So hopefully you agree that this is the same as what's left here. And now I've brought down this picture that I had from Wikipedia, which is what we were aiming for, remember, as the PDF for the final F distribution. Now remember, we're not quite at the F distribution. This is the PDF of our S random variable. Our final F random variable is a linear multiple of this. It's d2 over d1, which is why loads of these d1s and d2s are missing from the final formula. We'll get them in just a moment. But we're almost there. Here is this beta. Oh, and they've got this square root, but they've also finally done one final manipulation, which is to notice that 1 over, multiplying this square root by 1 over s times beta, this beta value, is the same as taking this square root and dividing it by that thing. So this is just a way of rewriting what we've got here. They're using x rather than s here, so you have to replace the s with an x. But then we've got, this bit is looking perfect. We've got 1 over the over x bit here, and the beta of d1 over 2, d2 over 2 here. And then this square root bit here is almost the same as what we've got here. So replace this with an x, and you've got x to the power of d1, which is what we've got here. Yes, okay, we're missing these bits, but they'll come with the final tinkering. And then, again, forget this bit and this bit. We've got 1 plus x here, which is what we've got here, to the power of d1 plus d2. So we're looking very, very good. So let's do the final bit then now. So our random variable t is equal to d2 over d1 times our random variable s. Now, d2 and d1 are both natural numbers, therefore what we end up with here is going to be a positive real number. We know this is the PDF of our s random variable for the positive real numbers. For 0 and the negative real numbers, the PDF is 0. Therefore, if we think about the range space of the t random variable, where this multiple that we're multiplying by is a positive real number, its range space where the PDF is going to be non-zero is also going to be the positive real numbers. For t is equal to 0, that corresponds to s is equal to 0, and for t is equal to a negative number, s is forced to be a negative number. Therefore, the PDF at those values for the t random variable is also going to be 0. And I apologise for calling this t. It makes it sound as though it's going to be t distributed. Remember, it is going to be f distributed with degrees of freedom d1 and d2. We've just called it t rather than f because we're using little t, and if I used little f it would just look bizarre. Right, so let's think about how you transform the PDF then for this positive part of the range space when we're just multiplying by a positive real number. So again, we can derive this result thinking with CDF. So if we think about the probability, if we take some little t, which is a positive real number, and we think about the probability that big T is less than or equal to little t, well, let's think about what range of S values would satisfy that. So if you plug in little t here, and you can find the little s that corresponds to that little t, so just by multiplying by d1 and dividing by d2, and then it's all the values of s that are smaller than that will then give even smaller values of t, i.e. in this range here. So we're actually wanting the probability that the s random variable is less than or equal to d1 times t over d2. Now, we want the PDF, this is the CDF for the random variable big T, so we want to differentiate this. We'll call its PDF f of little t, we'll call the PDF of this s random variable g of little s, so differentiate this with respect to t, and it will go back to the CDF evaluated at d1 t over d2, times, of course, the derivative of this thing inside with respect to t, which is d1 over d2. So this, then, is the transformation of the PDF when we've got this simple multiple transformation in this way. We just need to take this CDF here, and we need to evaluate it at d1 over t, d1 times t over d2, and then we need to multiply the whole thing by d1 over d2. So that's what we need to do to get the final PDF of the F distribution, and it will come out as this thing here.